Okay, when solving log equations, we're going to use a process called exponentiating. To exponentiate means to raise both sides of an equation to become the exponents of the same base. Okay, so in this first example, okay, before we can exponentiate, we need to first isolate this log base 9 of the quantity x plus 8 on one side of the equal sign. So I'm going to start by adding 2 to both sides, and that leaves me with 7 log base 9 of the quantity x plus 8 is equal to 5 plus 2, which is 7. Then we'll divide both sides by that coefficient of 7 to isolate the log base 9 of the quantity x plus 8 on one side of the equal sign. Okay, now we're ready to exponentiate each side by the base of the log. And recall that to exponentiate means to raise both sides of the equation to become the exponents of the same base. So I want to make the log base 9 of the quantity x plus 8 the exponent to a base that matches the base of the log. So I'm going to exponentiate using a base of 9. Okay, so I have 9 raised to the log base 9 of the quantity x plus 8 power. That is the inverse property. So I can bring down the argument of that log x plus 8 using the inverse property. Then on the right side of the equation, 9 to the first power is 9. And now I'm left with a linear equation. I can solve for x by subtracting that constant from both sides, and x is equal to 9 minus 8, which is 1. Okay, then my last step is always to check for extraneous solutions. If the answer is extraneous, that means that it doesn't check, but not because I made a mistake in my algebra, but because the answer is outside of the domain. So to check that answer, we can store 1 as the x, and then we're going to type our original equation just like it's shown here. Remember, the TI-83 has no way to enter a log base 9, so we need to use the change of base property. So I'll have 7 and then the log of the argument, x plus 8. Then that's divided by the log of the base, which is 9. Then minus 2. And 2 ways to check this. One is to press enter here and see if we get the other side of the equal sign, which we do. 5 is the same as 5, so we know that checks. Or we could do the equal sign from the test menu and then type in the other side. So we've entered the entire equation, and when we press enter, then we'd get a 1 for yes if it checks and a 0 for no if it doesn't, and we get a 1, so we know that x equals 1 checks as a solution. Okay, in example B, we're going to start by isolating the log expression, so we'll add 2 to both sides of the equation. And then the natural log of the quantity x plus 1. Recall that a square root is a 1/2 power, and that equals 1 plus 2, which is 3. Then I can use the power property to make that exponent of 1/2 the coefficient on my natural log. So now I have 1/2 natural log of the quantity x plus 1 is equal to 3. And then I'm going to multiply both sides by 2 to isolate that natural log of the quantity x plus 1. And 3 times 2 equals 6. Okay, now we're ready to exponentiate each side by the base of the log. A natural log is a log base e. So I'm going to exponentiate using a base of e. Then the inverse property brings down the argument of that log, x equals 1, and then that's equal to e to the 6th power. Then we can solve for x in step 3 by subtracting 1 from both sides, and x is equal to e, Euler's constant, to the 6th power minus 1. Okay, then that's my exact solution. If I am asked for a decimal approximation, recall we round those to 4 decimal places. So e raised to the 6th power minus 1 is 402.4288 if I'm rounding to 4 decimal places. So we've got 402.4288, and that would be my answer, approximate answer rounded to 4 decimal places. So then to check that answer, we will store it as x, and then in the original we have a natural log of the square root of the quantity x plus 1 minus 2 equals 1, and we get back a 1, and so we know that that answer checks. So go ahead and pause the video and try this application problem on your own. And then when you're ready to resume, we'll go over the answers together. Okay, so the speed of the wind S, which is in miles per hour, near the center of a tornado travels are related by the model S equals 93 log of D plus 65. So that's a common log. On March 18, 1925, a large tornado struck portions of Missouri, Illinois, and Indiana with wind speed at the center of about 275 miles per hour. And miles per hour is the units on the speed of the wind, which is s. We want to approximate the distance, d, traveled by this tornado. So we're going to substitute 275 for s, the speed of the tornado. So we'll have 275 equals 93 common log of d for distance plus 65. Okay, now we're going to isolate that common log by subtracting 65 from both sides of the equation, and we have 210 is equal to 93 times the common log of d. Then we'll divide both sides by that coefficient of 93 to isolate the log. So 210 divided by 93 is equal to the common log of d, the distance. Now we're ready to exponentiate both sides by the base of the log. A common log is a base of 10. So we have a distance then, using the inverse property, of 10 to the 210 over 93 power, and that would be the exact value. Then to approximate, we're going to need the calculator, and we'll take 10 raised to the 210 divided by 93 power, and we get 181.1609 to 4 decimal places. So 181.1609. And the units on that answer, since the wind speed was miles per hour, then the distance is going to be in miles.